Can you draw these graphs without lifting your pen? Can you cross every bridge exactly once? And what do 7 boys with the same last name have to do with graphs? Let's find out. In problem 1 we have 2 diagrams and need to determine whether it's possible to draw these graphs without lifting the pen and without retracing any edge. Let's start with diagram A. If you try finding a path yourself, you will likely realize that it seems impossible, but how do we actually prove that's impossible? After all, maybe there is a way, but we just haven't found it. Here's a useful trick. Forget about this specific graph for a moment and try drawing any graph that follows the rules. Once you've done that, label each vertex with the number of edges connected to it. These numbers are called vertex degrees. Now, focus only on the middle points, ignore the starting and ending points. Do you notice a pattern? Every middle vertex has an even degree. That's because every time we enter a vertex, we also have to leave it. So the total number of edges at each middle point must be even. This leads us to an important rule. A graph can be drawn without lifting the pen and without retracing edges only if it has at most 2 odd degree vertices, which serve as the start and end points. Now, let's go back to diagram A. Counting the degrees, we find that all 4 vertices have an odd degree of 3. Since we have more than 2 odd degree vertices, it's impossible to draw this graph following the rules. Now, on to diagram B. Checking the vertex degrees, we have 2 vertices with degree 3, 2 vertices with degree 4, and 1 vertex with degree 2. Since there are exactly 2 odd degree vertices, we can try starting from one of them and finishing at the other. Now, that isn't hard to come up with an appropriate pathway. In this case, it's possible to draw this graph. The key was analyzing vertex degrees. In problem 2, we need to determine whether it's possible to walk through a city crossing each bridge exactly once. This problem is based on the famous Königsberg bridges puzzle. Here, instead of working with a complex city map, let's simplify it into a graph. We represent the land areas as vertices and the bridges as edges. We've got the graph where there are 4 vertices and 7 edges in total. Notice that there are vertices which connected by 2 edges. Now, if we count the degree of all vertices, we got 5, 3, 3 and 3, which are all odd. Since there are 4 odd degree vertices, and we know that such a walk is only possible if there are at most 2 odd degree vertices, this means it's impossible to take such a walk. Euler proved this result in the 18th century, laying the foundation for graph theory. In problem 3, we need to determine how many edges exist in a complete graph with 5 vertices and n vertices. A complete graph is one where each vertex is connected to every other vertex by an edge. So, for part A, let's draw a complete graph with 5 vertices and count the edges. Instead of counting manually, let's use the general approach. Each vertex connects to 4 others. There are 5 vertices, so the sum of all degrees is 5 times 4, which is 20. But remember, the number of edges is twice as less as the sum of degrees. That's because each edge was counted twice, once for each endpoint. We actually established this fact in the previous video. So, here the number of edges is 5 times 4 divided by 2, which is 10. Now, for part B, we have a complete graph with n vertices. Here, each vertex connects to n-1 others. There are n vertices. The total sum of degrees is n times n-1, and dividing by 2, since each edge was counted twice, we get the formula. The number of edges equals n times n-1 over 2. This formula will come in handy in the next problem. Peter drew several points on a plane, ensuring that no 3 are collinear and connected every pair. Could he have drawn exactly 7 segments? From the description, we recognize that Peter drew a complete graph. The question is whether a complete graph can have exactly 7 edges. Let's find the number of edges for different number of vertices using our formula. For one vertex, the number of edges is 0. For 2 vertices, the number of edges is 1. For 3 vertices, the number of edges is 3. For 4 vertices, the number of edges is 6, and for 5 vertices, the number of edges is 10. Clearly, there is no number of vertices which results in exactly 7 edges. So, the answer is no. He couldn't have drawn exactly 7 segments. In a group of 7 boys, each has at least 3 others who share his last name. Prove that all 7 boys have the same last name. Here, let's represent each boy as a vertex in a graph and connect 2 vertices if the boys share a last name. Now, assume for contradiction that not all boys share the same last name. That means there are at least 2 boys with different last names. Let's color the vertices red and blue. Since each boy has at least 3 others with the same last name, both red and blue vertices must be connected to at least 3 others. But this means among the remaining 5 boys, at least 1 must be connected to both a red and a blue vertex. This means that this boy must share his last name with 2 boys with different last names. This contradicts the assumption, and the only possibility is that all 7 boys share the same last name. That's all for today's video. If you have further questions, leave them in the comments. See you in the next one. Bye.